is on black holes. And I say they're a natural conclusion of general theory of relativity. And we'll talk more about general theory later in the course. But it's really the concept of space not being an absolute thing, but it actually bends. Space bends and warps. And specifically in relativity is the idea that masses, objects with mass, create warps in space, changes in shape. So he predicted the existence, Einstein did. He died in 1955. Didn't actually see an evidence of a black hole until 1972. And of course, it's Stephen Hawking is an expert on black holes. I don't think he was the one to find that, but he is an expert on them. And like I say, it's just another example where his theoretical math, we've seen it. Okay, and I said recall the Higgs, just meaning that Higgs was, it's this particle that got found in CERN in Europe about 3-4 years ago now, and they predicted its existence in the late 60s, and they found it just recently. So that was a big deal. And the guy was just so happy to be alive to see the guy Peter Higgs, to see it actually get found. But anyways, that's irrelevant. We're talking about black holes here. Einstein was not alive to see them get found. There's two terms that we use, well, three on this page. Event horizon, and we call that the surface of the black hole. That's not exactly true. It's the surface where, like, inside of that event horizon, anything less than that, it's like is where, nothing can escape. And a singularity is another term that gets used, and it just means that at the very center of a black hole, we call it the singularity. Well, Stephen Hawking calls it the singularity. I just copy him. Okay, and then the other one is this idea of, it's called a Schwarzschild radius, and it's the distance from the singularity to where that event horizon is. Just looking at, a picture, the idea is that imagine these rowboats were light, and that if you're inside what we call the event horizon, light will just get sucked in. It can't escape. Remember I said earlier that one of the previous videos that it's like light's not fast enough to escape. Okay, if you're inside of here, the gravitational force is too strong, and light can't escape. The escape velocity is greater than 3 × 10⁸. If you can get past to here, like here, light can escape. And then, if you have something, there's a radius, which is the Schwarzschild radius, where if there is light there, that light will actually just go into orbit around the black hole, similar to anything else, if moving at a good speed around the Earth, right? Like at 42,000 kilometers above the surface at the center of the Earth, that's where satellites will go into orbit, right? Geosynchronous satellites traveling at 3,000 meters per second. It's kind of the same idea. If light was right here, it would start going around in a circle. And this is the idea we've watched videos like this. When you're sitting here, you could actually look one way and see the back of your head, because the light just would travel around in a circle. Anyway, so just looking at a little example with black hole, what if we wanted to find the Schwarzschild radius? What is the radius for a black hole that has a mass of 28 times our sun? Well, the piece of information you don't know, but I know, and you could always Google, is the mass of the sun, and it's 1.99 times 10 to the 30. So that's the mass of the sun, and then of course the mass of this particular black hole is 28 times that, so whatever that works out to. And V, the V you use in these questions is the escape speed, because we're going to use the escape speed formula, and it's going to be the speed of light. Okay? So the calculation is actually very easy. We're looking for R, so you just take the escape speed equation, rearrange it for R, and you get 82,000 meters. Which you say, oh, well, that's pretty big. It's about this distance from here to Toronto, and let's put that in perspective. That's saying that from here to Toronto, a radius of that would be, actually, no way, it's not even Toronto. It's like South London. Here to South London, forget that. Toronto's further than that. Here to South London. Inside that distance would be 28 times the mass of the sun. Like, it's an amazing, and this is the idea of infinite density. That's so dense, right? And that's why it's a black hole. Huge, huge mass in a tiny, tiny, tiny area. I mean, you think 82 kilometers isn't tiny, but again, think of 28 suns inside that area in mass. Anyways, that's I'm going to check mark it because I know that it has to be infinitely dense, but that is a crazy, it does seem unbelievable. But black holes kind of almost are. Anyways, that's a black hole type question I could ask you, will ask you. And you've seen everything you need to see now to do the assignment. You're going to struggle with it, no, for sure. And of course, I'll help you with it. And these are all the equations that you need. You're going to struggle with the scientific notation like me. And remember, you're kind of doing rocket science, so it's all good. It's all good.